Hi guys, we are continuing to talk about matrices, and in this lesson we're going to be talking about the identity matrix, inverses of matrices, and the determinant of a matrix. So that's kind of what we're focusing on. These are all three different sort of operations that make matrices useful. First of all, before we get into matrices, let's think about, do you remember what is the additive identity and what is the multiplicative identity? Those two phrases mean what number could you add to something that doesn't change the number, and what number could you multiply times something that doesn't change the number. So hopefully we all remember what those are. Additive identity is 0 because 0 plus anything is itself. So for example, 0 plus 5 is 5. Similar for the multiplicative identity, but not the same number, right? In this case, the answer is 1 because 1 times any number is itself. So again, for example, 1 times 7 is 7. Okay, well, matrices also have multiplicative identities. And the idea is if you multiply the identity matrix by another matrix, you get the original matrix. So just like with the multiplicative identity, we take that number times anything, it doesn't change the number. Same thing here, we take that matrix times any other matrix, it will not change the original matrix. And so here is a definition. This comes from the Big Ideas textbook that we've been using. But let's just take a look. Can you see the pattern? That most of the matrix is made up of zeros, except for down the middle, there's this diagonal where there are ones going down the middle. Same thing here. It's a little bit harder to see on the 2 by 2, but that's what's going on is essentially most of it's zeros, but then the ones going down are in this diagonal pattern are ones. And so we could go to a 4 by 4, a 5 by 5, a 6 by 6, whatever. It has to be a square matrix. But when we do that, that diagonal down the middle is all ones. And notice also it says in the definition here, if A is any n by n matrix, so it's a square matrix, and I is the identity matrix, then A times I equals A. In other words, it doesn't change it. And I times A equals A. So we learned in the last lesson that order does matter with multiplication, that for instance, matrix A times matrix B times matrix B does not equal matrix B times matrix A. So order does matter. In other words, this is not commutative. However, with the identity matrix, it doesn't matter whether you put that identity matrix in front of it on the left-hand side of it or on the right-hand side of it, it'll still work out to be the identity matrix. Okay, that also ties in a little bit with inverses. Do you remember what inverses of integers are? In an inverse with integers, it's just like a 1 over. So 6 and 1/6 are inverses of each other. And there's a couple different ways you can write that. When we write x to the negative 1 power, that means the inverse. And so x to the negative 1 is equal to 1 over x. And it also works the other way as well. That 1 over x, the inverse of that is x. And so these are inverses. And we know that inverses are helpful for multiplication because if you multiply the number times its inverse, you get 1. And as you know, we use that all the time. We use that with fractions, we use that with solving equations, we use it with so many things. So inverses, when you multiply two inverses together, you get 1. Well, the same thing with matrices, that if you have a matrix and you have its inverse, you multiply them and they get 1. And so that's kind of what it talks about here. Two matrices A and B are inverses when their product is the identity matrix. So rather than in this case, when we just had plain old numbers, it was 6 times 1/6 is equal to 1. When we have matrices, A times B, if they are inverses of each other, they're going to give us the inverse matrix, which is one of these up here, or again, 4 by 4 or whatever. But that's what it will look like if we multiply the original matrix times its inverse, it will give us the identity matrix. And so I'm writing this out in the margin because it's the same thing, but maybe it gives you an example. 2 by 3 by 3 matrices are inverses of each other. If matrix A times matrix B is the identity matrix for a 3 by 3, And to write out the identity matrix for a 3 by 3, remember it's going to be a square matrix, and it's going to have ones along the diagonal, but everything else is going to be zeros. And so it looks like this. It's a 3 by 3, mostly zeros, except for those ones along the diagonal. So when you multiply two matrices, if they are inverses, they will give you the identity matrix. Okay, there's a way to find the inverse of a matrix. And so this first concept that we're looking at is just finding the inverse of a 2 by 2. Look at this definition. It looks a little bit intimidating, doesn't it? We're going to go through it, but then I'm going to show you that your calculator is going to do it. So don't get too intimidated by this because your calculator can do it. Now, some of you might find that it's easier to do it by hand because the calculator has so many keystrokes, but let's just go through it. Okay, a to the negative 1 is equal to 1 over, and then they have this notation, and I will tell you right now that this is the determinant, and we are actually going to talk about the determinant a little bit more on the next page, but they define it for us here. So we can use this definition where they've got the determinant in there, or we can just use the one that's already spelled out for us. And then they have this qualifier, when AD minus CB does not equal 0. Well, if AD minus CB was 0, that would be undefined, so that wouldn't be very helpful. So that's why they're making sure that you understand that. Okay, let's go through an example to see what they are even talking about. We are going to look at this first example, and we are going to use this definition. So I can see from this definition that I need to start off by writing 1 over, and I'm making my fraction bar kind of long because it is long here, A times D. So in my original matrix, that's these two that are across from each other. That is 4 times 5 minus C times B. That's the diagonal going this way. So that's 3 times 7 times the matrix. And now I'm having to flip my matrix around a little bit. My A and my D switch places. So my 5 switches places with the 4. And my B and my C, they stay where they are, but they become negatives. So I'm going to keep my 7 and 3 where they are, but I'm going to make it a negative 7 and a negative 3. Now I need to go through and kind of simplify this because what I have is 1 over 20 minus 21, and then times this matrix. If I simplify that a little bit more, it's 1 over negative 1 times that matrix, and my negative sign is kind of getting lost in there, but that is a negative 3 and that is a negative 3. But we know, don't we, that 1 over negative 1 is just equivalent to negative 1. So we're going to take negative 1, and because it's a scalar times a matrix, we know how to do this. We're just going to take negative 1 times each member of each element inside the matrix. So that's going to be a negative 5, a positive 7, a positive 3, and a negative 4. Okay, I don't know about you, but that seems like a lot of work. But that is our final answer. Let's do one more example just so we know what's going on. Okay, so we're going to take 1 over, and we're going to multiply 5 times 2, which is 10, and subtract 3 times 4, which is 12, and we're going to multiply that times the 5 and the 2 switch places. The 3 and the 4 stay where they are, but they become negative. And so that simplifies to negative 1/2 times 2, negative 3, negative 4, and 5. And so now again, because this is just a scalar times a matrix, I can just multiply. Negative 1/2 times 2 is negative 1. Negative 1/2 times negative 3 is a positive 3 over 2. Negative 1/2 times negative 4 is a positive 2. And negative 1/2 times 5 is a negative 5 over 2. And so this final answer is the inverse of B, is this one. And the one we came up over here, that's the inverse of A, is this answer. Okay, that's how you find the inverse of a 2 by 2 matrix. Notice we only did 2 by 2s, and as we know, matrices can get much bigger than that. It gets even more complicated, so we're going to stop with doing this by hand at the 2x2s. I'm not going to go into 3x3s by hand. Before we turn the page, make sure that you go into your margin and write down any questions. If there's anything where I lost you along the way, write your questions down in the margin so that tomorrow in class you can ask questions and we can help you out. Okay, let's turn the page.